In 8.2, we study surfaces of revolution, more specifically, the area of a surface of revolution. This section is going to feel very similar to arc length. In fact, uh, we need arc length in order to find surface of revolution. So let me explain. We'll just kind of explain where the formula is going to come from. Okay, so imagine you've got the frustum of a cone. Okay, so it's a cone with the top chopped off, if you will. We call it a frustum. Okay, and so we're going to say that it has two radii, right? The upper circle has radius 1, the lower circle has radius 2. And then we need a name for this angled side here. We call that the slant height. And for some reason, it goes by capital L. Maybe S is too common of a letter, so they just took the next letter L. I don't know. A capital L for the slant height. So you may remember from geometry, or maybe you don't remember the formula for the lateral surface area, just the surface area around the outside, not including the circles. It would be this. The surface area, the lateral surface area is 2 pi RL. And you kind of think like, okay, the L makes sense, 2 pi because we're spinning around, but what's the R? The R is the average of R1 and R2. So kind of a cool formula there. Looks a lot like the formula for the lateral surface area of a cylinder, right? If these were the same radius, top and bottom, we'd have a cylinder, and then the average would just be the same value. So kind of same idea here for the frustum of a cone. Okay, how is this going to come in handy? So imagine I've got this all drawn out. Gonna try and keep some of that on the screen maybe. And I'll just show you everything here. So imagine that we've got some curve. Okay, and I know there's a kind of a lot of lines and stuff going on, but you can kind of see that curved function going through. And think what we'd like to do. We would like to revolve that curve around the x-axis. And so it would create a three-dimensional shape. And what we'd like to know is the surface area. So in Calc 1, we did the volumes of these kind of shapes. So now we're actually taking it up to a more difficult level. The surface area is even more advanced than just the volume. So we're spinning this around, and kind of where it dips down, right, it would spin back the other way and create kind of this cool curved figure that sort of pinches together where it crosses the x-axis, right, if you imagine those parts spinning. Okay, but what we want to know is the surface area of such a thing. Okay, so I've broken this up like, imagine this is A, this is B, and I've split it into 4 sub-intervals, right? 1, 2, 3, and 4. And then I've drawn the points at each of those locations. And then we're going to connect those with straight lines, just like we would do with arc length. But then now we don't want to find the lengths of those. We want to think, okay, this thing is revolving. So as that length right there rotates, right, it creates a frustum of a cone, although it's, of course, sideways. Then you start to connect the dots, to the drawing here, and well, that would be like radius 1, radius 2, and then that length right there would be the slant height L. Okay, so we know from our studies in 8.1 on arc length that L is the distance between like x1, x2, y1, y2, right? So it's the square root of delta xi squared plus delta yi squared. We saw that explained in the previous section, so let's just jump right to that. And then we also saw explained, I'm skipping all the algebra here since we did it already, but it would work its way down to L equals the square root of 1 plus f prime of x squared delta x, right? In the same way that it did for arc length, well, it's going to simplify in the same way here. Okay, well, we pretty much have it. once we recognize that L gets replaced by this, that would go in right there in the formula. Okay. And then R, well, R, what's happening? So we call it the average of R1 and R2. But think if there are infinitely many subintervals, then they're infinitely close together. So if these two lines are infinitely close, then we can say the average of the two radii is really just the radius itself, since they're merging together. So where here we have radius r, all we got to do now is put r of x. And because we're adding all of the infinitely many little surface areas together as we go along, right? That's an integral. That'll do that for us. So we can pull the 2 pi out in front, 2 pi integral from a to b, r of x, and then our square root 1 plus f prime of x squared dx. That is the formula for surface area. Okay. Pretty cool. All right, let's put it to work. We'll get to our first example right here. Okay, I'll try and not show you too much. So it says find the surface area, and again we will round these to 2 decimal places because typically final answers are not pretty things with these either. So we're going to say it's the region bounded by y equals the square root of 9 minus x, y equals 0, x equals 0, and we're going to rotate or revolve about the x-axis. So let me go ahead and show you the drawing. Show you a lot of work here, and that's okay. We'll talk through it. So right over here in my first drawing, I've graphed square root of 9 minus x. If you're not real sure how to do that, if you're a little hesitant, using Desmos, right, desmos.com, you can type that right in and get the graph. So it turns out it's a square root pointed back the opposite way starting at 9. So there you go. And then we also have the lines y equals 0. Well, that's the x-axis. X equals 0 is the y-axis. So what's the region they're talking about? It's right here. Okay, so we're going to take that and we're going to spin it about the x-axis. Okay. And really, you know, I've kind of drawn it as the region. The truth is we're just taking the arc and revolving around, creating just the 2-dimensional surface through a 3-dimensional space. Okay, so here's a simplified drawing where we just have the curve rotating, and okay, so I've labeled where does it pass through here. Well, it's at 3 is where it would pass through, x equals 0. And we've got the 9 there. Okay. Now, if you're wondering, you know, like what's the big difference, you know, between what we're doing here and what we did in surface area, and the big difference, right, is this r of x. The rest of it looks familiar. So what is r of x? So it's the distance from your axis of revolution to the edge of your surface. So here the axis of revolution is on the x-axis, and here's, you know, here's the curve, here's the arc. So we got to go from the axis of revolution pointing perpendicular out until we hit that curve. And that distance right there is our radius. Now we call it r of x because, of course, it will change depending on where we look at it. And so it's a function. Okay, we'll come back to that. First, let's go ahead and find f prime of x to plug into our formula. So y, right, there's f of x right there, 9 minus x to the 1/2. If we take a derivative, 1/2 9 minus x to the negative 1/2 times negative 1. And I would prefer myself, I prefer to think of it as negative 1 over 2 square root 9 minus x. Why do I prefer it written in the fraction form with the square root? Well, because we're about to square it. And this squares very nicely. We get positive 1 on top. And then 4 and then the square root cancels. 1 over 4, 9 minus x. Okay. At the same time, let's identify r of x. In this question, r of x, if we're coming off the x-axis going straight up, it might be simpler than you think. R of x is simply the function. This function is describing how far up you are at any given x value. And so there it is. R of x simply equals the square root of 9 minus x. What is the radius at any given x value? Okay, so we'll take these two pieces, plug them into our formula. And we get this right here. Let's also note just our limits of integration. So you see that 0 to 9. And well, it's with respect to x, right? So 0 to 9. It's kind of nice to see that in the picture. So we've got surface area equals 2 pi integral from 0 to 9. And then there's our r of x, square root 1 plus, there's f prime of x squared dx. Now, if we've made it this far, we're doing pretty good. Where do we go from here? Well, of course, now it's just a matter of can we perform this integral? And this one is actually maybe not as bad as it looks at first. We're going to simplify it. If we're multiplying two square roots, we can put that all together under a single square root. So let me show you what that would look like. Surface area would equal 2 pi integral 0 to 9, and then you notice I just put one big square root around both of those parts, and those will multiply together. Now this works out really well. Imagine distributing the 9 minus x, so 9 minus x times 1. 9 minus x times our fraction, right, would cancel nicely. You don't have to FOIL it. I highly recommend you don't. We'll end up with square root, and well, if we multiply by 1, 9 minus x, we multiply by the other, it works out to just be plus 1/4. There we go. Okay, what can we do from here? Well, we could combine the 9 and the plus 1/4, but I'm actually going to do things in a slightly different order. Similar to what we saw back in the integrals with arc length, I'm going to say, you know what, I see that 1/4. I'm going to factor out a 1/4 from everything underneath here. Okay. And that's going to make my work a lot easier. So surface area equals 2 pi integral 0 to 9, factoring square root, factoring the 1/4. I got the 1/4 there. If I factor 1/4 from 9, I get 36. Factor it from x, I get 4x. And plus 1. So if that 1/4 was to distribute back, right, we'd have the same thing. Then I can pull the 1/4 out of the square root to be a 1/2, and even pull it all the way to the front. So our 1/2 would cancel with the 2 very nicely. Integral 0 to 9 square root, and why don't we just go ahead and add the 36 and the 1. So square root 37 minus 4x. And that looks a lot more manageable than what we started with for sure. Now we just got to think through, is this going to be some kind of a special integration technique? Or is this something that should be more familiar to us? And it's actually more familiar. This is just a U sub. Can you believe the number of U substitutions in this class? It's out of hand. And they just, mesh with all the other styles. Okay, here we go. So u equals 37 minus 4x. So du is negative 4 dx. And I like to just divide that negative 1/4 over to the other side. Negative 1/4 du equals dx. And so here's the new integral in terms of u. Surface area equals negative pi over 4 integral 0 to 9 u to the 1/2 du. And taking an antiderivative, there you go. Then plugging the u back in. I know I'm going way too fast, but hey, it's on video, right? And at this point, we can go ahead and plug the 9 in, subtract, plug in the 0. So it turns out plugging in the 9, I'll just show you the final answer. Plugging in the 9 is really nice because that'd be 37 minus 36, and 1 to the 3/2 is 1. Then we subtract, plugging in the 0, well, that'd just be 37 to the 3/2. So in the end, when it's all simplified, negative pi over 6, 1 minus 37 to the 3/2. Well, we could leave it like that, I guess. But I think for these answers, we kind of like to have a decimal number, so it's a little bit easier to wrap our head around 117.32, and that's our answer here. Let's stop this video. More to come.